Thank you very much for inviting me, Barbara and Patrick. It's very nice to be here. And it's actually sort of fitting to follow Peter's presentation because of, he's done a very sophisticated job in 3D. And actually, I'm going to go back to 1D models and see if we can learn something about the evolution of the flow and how it relates to heterogeneity. Perhaps following exactly through some of what Peter said in terms of what we need to know to make a time evolution of the flow and learn something about what's happening today, actually precisely predicting some of the observations. One of the things we need to know is, what is the origin of the heterogeneity? Specifically, the seismic heterogeneity, if we're going to use seismic tomography to initialize, a seismic model, even if in an iterative fashion. So the origin of heterogeneity, what you see in seismology, right? It's a combination of the. It's a combination of several things, right? Temperature, composition, and also phase transitions. And the fact that phase transitions give rise to lateral variations in seismic velocities is something that Don Anderson, talked about a long time ago. Right, and through these processes of differentiation and melting, you can interact the temperature and the composition, and also the phase transition. So this says a lot about the origin of what we might see in seismology, which is of course origin of the major element heterogeneity that you might observe. However, one of the sort of vexing problems in terms of understanding the temporal evolution of the flow and the chemical evolution of the mantle is that, in fact, if we look at the minor element heterogeneity, the stuff that you see from geochemistry, for example, in this diagram of Hart et al., where we have different end members on the isotopic, so this isotopic ternary, DMM, high mu, EM1, EM2, or quaternary, whatever, is that sort of isotopic heterogeneity, which is persistent and you have to be able to preserve, is difficult to relate in terms of geometry and location to the seismic heterogeneity that we see, right? And so there have been, as a result, sort of many ways, and as illustrated in this cartoon by Paul Tackley from 2000, to try to relate the isotopic heterogeneity that you see, so the minor element to the major element, because we have to preserve it and we have to evolve it. So, for example, in the purple are regions of, say, of primitive material or reservoirs of, sort of something that has a major element compositional difference and also gives rise to isotopic differences as well. You can, of course, create heterogeneity continuously. This is what we do through mantle convection and plate tectonics, which is the melting at the ridge and introducing the heterogeneity, both thermal and chemical, into the mantle. How, however, to preserve some of this heterogeneity so that you can see long-term in the evolution of the Earth the sort of, this distinct chemical heterogeneity? Well, this is done here through having isolated reservoirs that perhaps have a distinct compositional inherent bulk compositional difference, right, and might lead to layering of the flow. So dynamically, one way to do this is to be able to isolate the regions so that they don't participate necessarily in the flow, but they are sampled somehow by other sort of mantle flow features. And so one example of layered convection is shown here. This is on a paper by Paul Tackley in 1993, where in this state you have an unlayered mantle, so full mass transfer between lower mantle and upper mantle, and another in which you have, in fact, intermittent layering, where you get the lower mantle partly isolated from the upper mantle. And of course, in this case, if the layering is actually not induced by inherent compositional difference, bulk compositional differences, like the purple sort of blobs implied in the previous cartoon, but is in fact induced by the presence of a phase transition, one of the origins of sort of major element heterogeneity. So in this particular case, sort of there is a very large Clapeyron slope, which gives rise to layering or intermittent layering in the mantle. This is something, of course, that I've been aware of for a very long time, including the absolutely spectacular papers by Christensen and Ewan, sort of defining the effect of the 660, for example, would have on a slab penetration. So why should phase transitions give rise to layering of the flow? So in terms of thermodynamics, in a first order phase transition, you are going to get a change in the density. It's not a compositional difference. You have the same composition, but you change structure. That structure changes to a more compressed state, a highly closed pack, and you get a different crystal structure. The different crystal structure gives rise to different properties, right, including a different density. So this, from a very nice review paper by Facenda and Dalzilio, you have two regions here, say in a simple olivine system, and you have a hot region and a cold region, so a slab and a plume. The colors here represent the buoyancy, so the delta rho. And what you see is that when you go through different phase transitions, you can increase the density or decrease the density, and that this effect will be different depending on the phase transition. Now, in a simple system like olivine, single crystal, this will be just reversed from each other, right? And you can see that in terms of the buoyancy, which is what it says here, I apologize for the conversion, just made everything blurry. You can actually see that there are very distinct differences here, right? So what's changing in this particular case, or what has most of the effect, is the density change. But another thing that is very important in phase transitions is because they're chemical reactions, you actually have a latent heat, right? So you can have a latent heat release or a latent heat absorption. And you can see this in the energy equation. This is the formulation in one of the new 3D convection codes. This is in aspect, the formulation here. This is what you might recall traditionally in terms of the energy equation. So the diffusive terms here, the rate of change, the advective term, and the heat generation term. Here, this is frictional heating. But here are two things that come from compressibility, which you need. Obviously, you're going to have phase transition, the adiabatic compression, and also the latent heat effect. And so the latent heat effect, which affects the geotherm and it affects the phase transitions, is something that you have to take into account. And, of course, the change in the properties. Now, of course, the mantle isn't made of olivine, and we've known this for a long time. This is blurry, but perhaps this is appropriate in a multi-phase mantle. And so here at the top, it's, say, Harzburgite. Here's pyrrolite. Here is a morb. And you can see that the phases are very different depending on composition, of course, and they're different in the upper mantle and lower mantle. And what you'll notice is that there's a huge amount of variability in the upper mantle. Okay, so what does this do, having multiple phases and having multiple properties? So again, if we go to the paper by Facenda and Dalzilio, we can see that from the olivine system to one that, say, has a mechanical mixture or Harzburgite and morb, and where this is the delta rho, again, in the red and blue colors, this is the compositional differences, that if you compare this is the slab buoyancy in purple, this is the plume buoyancy in orange, they become quite different as a function of depth because of the presence of the different phase transitions. In fact, you can almost eliminate the 660 because of the garnet to perovskite reactions. One other way to see it, for example, is as a function of depth in the top 800 kilometers, is to look at the d log rho dt, so the logarithmic derivative of the density with respect to temperature, and you can see that it's enormously different because of the presence of phase transitions. You also see a background in here, which is the depth dependence of the properties, what Lars likes to call the isomorphic part, where these little changes will be the metamorphic part. So it's clear that we want to have to see the compressible effects, which Peter talked about. If we want to see, how these phase transitions generate heterogeneity and how they might affect the flow and layer and lead to the preservation of heterogeneity, that we need some sort of first thermodynamic model to tell us about the properties in the interior. This is, of course, something that Lars and I have been working on for now. Well, I don't want to say how long, but we need something that combines traditional petrology, which is the free energy minimization to find the stable phase assemblage, which is a function of pressure and temperature, with traditional mineral physics, which gives you the physical properties. And so this is the essence of Hephaestus, our code, where we do Gibbs free energy minimization right here, subject to the constraint of fixed bulk composition. So it is for fixed bulk composition, you self-consistently minimize the Gibbs free energy, get the phase assemblage, and calculate all the physical properties. I should say this is a thermodynamic equilibrium model, so it calculates the static properties, so alpha, Cp, and so on, and not the transport properties, which are equally, if not more important, in convection. Okay, Now, many people have done this before. You know, our big achievement, if you want, in this is the anisotropic generalization, so we can do individual elastic constants, but I won't talk about that now. In terms of the dynamics, what are some of the interesting things that are going on here? So in terms of the dynamics, you know, we could sort of maybe focus on one physical property of interest, which is the thermal expansion. Why? Because regions of negative thermal expansion are regions where convection is unlikely to occur because of the adiabatic gradient that you have there. So in this diagram, which is focused on the upper mantle temperature versus pressure, you have here all the phases that are stable. So this is a phase diagram in the back. And in the color, the contours is the thermal expansion. So what to notice here? To notice here is there are many regions where you should have a negative thermal expansion, and regions that you actually can't see either, that are very difficult to represent because the phase transitions are so sharp, sharper than the 10-kilometer resolution that Peter was talking about, that in fact you miss them altogether, even it's the representation. But they can have enormously large negative thermal expansion and therefore should have an effect on the flow. And that's not something that's easy to capture. You can also see here that the phases change dramatically with temperature, right? In the upper mantle, but this is true in the lower mantle as well. So that, for example, at very high temperatures, you go from olivine to garnet, right? Skipping sort of the perovskite altogether. Now, as we showed before, you know, this does have an effect on the flow. This is, again, from the paper by Facenda and Del Zilio. This is a plume at the top. This is the original sort of slab. Sorry, plume. I meant slab. Original slab at the top. This is after 20 million years, I think, or 12 million years right here. And the background is sort of the density field, the initial temperature field. And you can see in this particular case that the slab does seem to lay down, be impeded, as it has been shown before, by the phase transition. And, but I can tell you that this isn't the only effect, right? The rheology is equally important, you know, and other assumptions about the age of the plate and so on. So does it in fact matter that we have a multi-phase mantle? Does it matter at all? Does it give you anything in terms of layering? Okay, so there are some very nice papers on the introduction of self-consistent thermodynamics in 3D convection by Nakagawa and Takli and others. And basically, they find that, yes, it has an effect, especially if you're looking at compositional thermochemical convection. But in fact, the differences in terms of average properties aren't that large, and that there isn't not much induced layering for today's conditions, starting from the potential temperature that we expect in the Earth today. But the question then is, has this always been the case? Because the Earth has been cooling. And if we have a huge temperature dependence on the phases, was the Archean mantle the same as today? Allegre argued that, in fact, things aren't the same today as they were in the past, sort of going back to the chemical heterogeneity that we talked at the beginning, that, in fact, there could have been layering in the past that helped preserve the heterogeneity today, and that mass transfer, complete mass transfer, as we see today, may be a recent phenomenon. Okay? And he argued that the transition would be caused by cooling and the reduction in the Rayleigh number. Okay. So, do you expect an effect? And so all of this is said temperature dependence. Again, just now this is the whole mantle, just to point out the temperature dependence of the phases, right? You see an enormous difference as a function of temperature at the same pressure in the phases and the phase transitions you expect, and the amount of the negative thermal expansion at the different phases. So in fact, if you cool the mantle, you should expect to go through different phase assemblages, and that has important implications for the geochemical evolution as well as the sort of dynamical evolution. So instead of going through and doing a full 3D model with secular evolution, which means varying the boundary conditions, which we normally don't do, the temperature boundary condition, we're going to do through a very simple 1D temporal evolution model with the innovation that we're going to do this by adding the full thermodynamics to the 1D model. Okay? And so we've constructed a 1D model of the Earth once it has solidified to examine the thermal evolution of the mantle and core, and we're using our model to track the mantle properties. And we track the state variables, temperature and pressure, rho, alpha, and Cp we get from Hephaestus. We use a thermal conductivity from the literature and a Arrhenius form of the viscosity, and we fit the equation of state of the core to Prem. Now, I'm not going to talk about the core very much anymore because it actually has very little effect on the mantle and it's beyond the scope of this talk. Anyway, so these very simple 1D models, these thermal evolution, they've been done before. They haven't been done with the thermodynamics. You ask, is it useful? And I hope to show you that that's the case. So we start with an initial temperature profile shown here. This is as a function of radius here, temperature. It's an adiabatic temperature profile with a jump at the core mantle boundary, which is one of the most important things in the model in terms of determining evolution of 1400 K, determined from both the present-day geotherm and the melting of the core. An initial potential temperature about 2000 K, so say 400 K hotter than today, and some thermal boundary layer where heat is lost by diffusion. Okay, so things are adiabatic. The initial state, you have to iterate the pressure, the gravity, and so on to get to a proper initial state. This is this says etc., not et chi, okay. So now, what do you need to solve for the one-dimensional temporal evolution? You need to solve the energy equation, and this is in spherical coordinates, the radial term. So the interesting thing here, this comes from several papers, it's been around for a long time. The method that we're using is to use mixing length theory, okay? And the critical thing to understand about that, so this is your typical energy equation, the variation of the derivative temperature with respect to time. This is the diffusive term. And now we have a convective term, okay? And this is where the mixing length theory comes in, plus some internal heat generation. So basically, this is a way to parameterize convection. Okay, this came from trying to look at turbulence, for example, where we have the gradient of the temperature minus the adiabatic gradient square. Sorry, this sort of disappears. I'm not sure what to do. Okay, and so where is the sort of mixing length term? It's in the K sub V term here. And here what we have to do is parameterize it in terms of the fact that if you have if you have a condition such that you have a negative thermal expansion, so you have a positive thermal expansion, you get convection, otherwise you don't get convection, right? And the mixing length comes into here, right here. This, we can go through after the talk. This comes partly from the Stokes settling velocity. You'll recognize some of this form here, but you see that the mixing length, or the critical length, if you want, is to the fourth power. So it is actually a very important term. So basically, there's no convection if the system is subadiabatic. Okay? Now, what is the critical length scale? So in the papers by Kimura et al. and Takeshima and others, okay, the mixing length is the critical length that makes the Rayleigh number and the Nusselt number agree. Basically, sort of the vigor of convection and the heat distribution. And so there's a relationship, there's an exponent to the 1/3, and you have to pick a mixing length that lets you agree with that, okay? So the way this is done is by calculating the L to the nearest boundary. So it would be either to the core mantle boundary or to the surface. And so, in fact, what we're going to do is we're going to do 3 different cases. One in which we actually let L be the entire depth of the mantle. This is this curve right here, okay? Another where we just pick it in terms of the sort of nearest boundary, say the 660. And another which is we can call the double or layered convection. Another where we allow L to vary dynamically according to a local flow criterion, meaning we keep track of where the adiabatic gradient is subadiabatic, where there is no convection, and determine L that way, and we let it vary so that we have intermittent layering. Now, the form of the equation that I showed you, right, didn't actually have the compressibility term. But we need that compressibility to be able to introduce those proper effects of adiabatic compression and also to track the thermodynamic properties. So this is done quite easily by determining, sort of simple differentiation. It's not dt dt, it's dt rho cpt, and so simple differentiation gets you a compressibility term that we can find from the thermodynamic data and divide the equation by that. Okay, so that's sort of the setup of the theory. I hope I have a few minutes left. Yeah. Okay. And so some validation. Again, I apologize. This is from the convergence. So for initial potential temperature, 2000 K. So for 100 K hotter. Okay. So does the model work? Does it evolve to something that is at all reasonable? Okay. So we have depth here, and we have. I can't see without glasses anymore. So this is VPVS, and this is density. Okay. In black, it's Prem. And here is single layer in blue and double layer convection, so those extreme members that we're talking about. And for single layer convection, you end up agreeing with Prem pretty well. That's probably more a function of how good Hephaestus is than anything else. We disagree in VS, or how bad Hephaestus is. Okay, so I think that, in general, we're doing okay. We're not going to match it perfectly. This is a very simple model. The heat flow that we're getting out of the core mantle boundary is within the estimates, for example, of 5 plus or minus 5 terawatts. We're getting about 7 for a potential temperature of 2,000, initial potential temperature 2,000, and a surface heat flow that is a little low, 35 terawatts, but we haven't accumulated any radiogenic heat in the crust or anything like that. So it's actually also, for the first order, not a bad estimate. How do we do? We do this, this is a finite difference scheme. It's a second order Runge-Kutta scheme, but it's, you can try first order and fourth order, it makes no difference. The delta R, so in how many steps you do it as a function of depth, is about 10 kilometers, and the maximum delta T per time step is 0.1 Kelvin. Okay, so let me show you some results. What you see here is, again, T as a function of R, so the radius of the mantle versus the initial versus the temperature. You start out with the initial potential of 2000 K. The curves here represent time evolution. So blue is 0, this is 1.5 gigayears, this is 3, and this is 4.5. And this is the layered case, and this is the unlayered case. Just as two sort of end members. This, of course, has been seen before. This isn't really the point, more to show you the behavior. The upper mantle cools rapidly in this case, as it should, but consequence actually of some of the Arrhenius rheology. The lower mantle remains insulated, so that could lead to preservation of some heterogeneity if you have it there. In the case of single layer, you reach steady state incredibly quickly. That's because of the temperature dependence of the viscosity. Okay, but, okay, this is, sort of the very simple case, but look at the time evolution. If we superpose that time evolution, starting at a potential temperature of 2000 K at 0 million years, okay, and then the others 1.5, 3, 4.5 billion years. This is depth, this is temperature, and this is the equivalent of the thermal expansivity I showed you before, right? This is the adiabatic gradient. In regions of the negative adiabatic gradient, you should get no convection, right? And what you can see from the secular evolution, this is not unexpected, right? Given the phases that are changing, you actually should go from places with a negative adiabatic gradient and therefore no convection to actually convection. And so you should go you should go through layering state and non-layering states. And because we're not adequately capturing it here, there can be layering at other depths, but you can't see it because these might be one grid point, but very sharp phase transitions nonetheless. Okay, so what's happening is that as the system evolves, you actually are going through different phase transitions, different physical properties, and the system goes into a layered state. So those two end members, somewhere between those two end members at any point in time. So one way to represent that is in these two graphs right here. This is the temperature gradient that you would need to overcome the negative thermal expansion, so you get convection. So given the temperature gradient that you've gotten out of the evolution, given the fact that you have the negative thermal expansion, okay, this is the amount of temperature gradient you would need to actually overcome the fact that there's no convection. So add it to it. So it's right here, and then here is, as a function of time, 0 to the present day. So in red, these are intermittent layered states. Right, they're layered states. So there's a lot of intermittent layering, and in fact, a huge amount of time is spent in that. And then this is the heat flow in the transition zone, out of the transition zone. And in red, again, would be the layered state, and in blue, the non-layered state. They don't correspond perfectly in time. But the main point is that you spend a lot of time in the layered state. Okay? So just like Allegro proposed, but for different reasons, we actually are getting layering. Okay? And in fact, the system spends about 80% of its time in the layered state. So the layering arises naturally from thermodynamics, for the fact that we have, sort of different physical properties, different phase assemblages, which should affect actually the melting that you get as a function of time. And it doesn't depend on the Rayleigh number. But if you have layering and you're spending a lot of time in the layer state, you can preserve those reservoirs that we talked about at the beginning, even though you still might get some mass transfer between upper and lower mantle. And just to conclude, I have just 2 more slides, right? If we want to look at the preservation of heterogeneity, right, we can track not just the diffusion of temperature, right, the temporal evolution of the temperature. We can also use mixing length theory to track the evolution of the mass, right? So use some sort of tracers. And so we can recast the equation for the diffusion of mass in terms of mixing length theory, which is what you see here. I won't go through here. And then basically just advect tracers when there is layering, when there is no layering, and see what you get in terms of the mixing time and the possibility of preserving heterogeneity. So this is just a preliminary result, and one example, right, is that you have some amount of tracers in the bottom half of the lower mantle. This is the initial distribution in blue, just like the time. And then as a function of time, 50 million years, 150, 500 million years, how that is evolving. And so this is the mass concentration as a function of time. And it takes, the mixing time would be however long it takes for the differences between these two to be less than 10%. But those thresholds matter. So what you see here is, in fact, at least in the way we've done it preliminarily, the preservation of heterogeneity isn't that likely because from layering, but partly because we haven't accounted for everything, and partly because the system is still having some mass transfer through, and so the mixing timescales are about 100 to 300 million years, which isn't enough. But the potential here is great, right? So where are we going with this in the future? This is just an examination of the possible physics of it. One is to keep examining the mass transfer, really get down to what the mixing timescales might be, especially when we solve all our problems in terms of how we do the traces and the threshold. But obviously, just like Peter showed, and even forgetting the adjoint, we really need to go to systems that have three-dimensional convection, obviously, because the dynamics does change in 3 dimensions, with the full thermo, right? Meaning with all the compressibility effect, all the depth dependence, but also allowing for the secular cooling, which you can get from the 1D models, which has been done before with the thermodynamics. However, one of the things that's extremely important and that hasn't been done, right, because it's difficult, because it's computationally expensive, is to be able to capture the very sharp phase transitions, right? And when I say sharp, I mean sharp, right? The 660 is probably about a kilometer or a few kilometers, right? And this isn't the only one that is sharp. So what you need, obviously you can't do it. You heard Peter say what the computational expense is, okay, in that case the adjoint, but even if you don't, so you need some sort of mesh adaptivity, like aspect and fluidity, that it's essential. And then it has very large implication for the Earth's geochemical evolution. Thank you.
Thank you.